If you recall, last week was spring break. The week before that, last week, modulo this class. 2 weeks ago, we introduced the idea of vector calculus. The calculus part we already know. We know the kinds of things that we're going to be doing. Slope of the tangent, maybe normal to a tangent plane, slope of a tangent line. And integration is multiplication, but one of the factors is continuously variable. So here's our first category in line integrals, and we're going to go over the elements that we need, but I want the context to be in place. And line integrals is where we integrate a vector field over a curve. Recall that a vector field is just a function where the output is a vector. And we're going to, the first step is we're going to integrate a vector field over a curve. When we perform an integration, when we do an integration, we have to integrate over a set. In a simple integral, it's over an interval. In a double integral, it's over a region in the XY plane. In a triple integral, it's over a solid in three-dimensional space. Here, we're going to be integrating a vector field over a curve, a one-dimensional curve. It doesn't have to be just in R2 or R3, but we are going to be working in R2 or R3. So the curve is just going to be a one-dimensional set in R2 or R3. Here's our notation. Our notation is exactly as it says on the tin. The new thing that we have is that the multiplication is a dot product. That's the dot product that the multiplication that we have for a line integral. Integration is multiplication, but one of the factors is continuously variable. In this case, since we're dealing with vector valued functions, our multiplication will be in the form of a dot product. This part of the integration notation, the integral over C, that's telling us what we're plugging in to f dot dr. So C is the curve. This is the set of points. That's the set of points where we evaluate our product. Just like when we said the integral from a to b of f of x dx. It's all the values where we calculate f of x dx. We plug in all the real numbers from a to b and add them up. We're going to do the same thing here. At all the points along the curve C, we're going to evaluate f dot dr and add up the results. One thing to note is that our multiplication is the dot product, and so this is going to produce a scalar. And so eventually we're going to have to know what that scalar represents. So one thing we want to note is that this will be some scalar. This will give us a scalar because we're calculating this. We're just adding up a bunch of dot products. We'll have to know what that scalar represents in a particular scenario, but we already know what the dot product is about. The dot product is multiplication at an angle. Dot product is multiplication at an angle. That's what we've added in this line integral business. In the integral from a to b of f of x dx, the f of x and the dx were just scalars. They didn't have direction. We weren't losing something because the factors were not going in the same direction. Now, the factors might be going in the same direction. That reduces how much of the product we get. Do we get 100% of the product, 0% of the product, negative 100% of the product? As theta goes from 0 to 180. So the dot product is just multiplication at an angle. And so that's the new thing that we've added here. Other than that, the notation is just like it always is. Oh, there's one last thing. The dr is a small piece of the curve C, just like it always is. The dx is the small piece of the interval from A to B. So in this case, the dr is some small piece of the curve C. The dr is some small piece of the curve C because that's what the D thing always is. It's the dx, a small piece of the interval from A to B. The dA, a small rectangle in the region R. The dW, a small rectangular solid in the solid W. The thinking is the same as our original integration. We're going to, for this small piece of the curve C, assume that the vector field is constant. Do our multiplication, move on to another point, do another multiplication, add up the results. The thinking works the same. Is everybody okay? Here are the things what we have to be able to do. We do have to be able to parameterize a curve. That's the first thing what we need to learn. That's the first element that we need to deal with. We need to figure out how we are going to describe the curve so that the integral can understand what we're plugging into it. We're going to start with our favorite parameterized curve. We're going to parameterize a circle of radius r. We know we have various ways of describing a circle in R2. Oh, let's do this in R2. We already have descriptions of a circle of a given radius in two-dimensional space. We could do this with a function. Well, we need two functions, plus or minus the square root of r squared minus x squared. Or is the top and the bottom. Or we can right left it, I said plus or minus. Another way to do this would be with an equation. I'm going to give the circle. 5 was the easiest thing to turn an R into. I needed to drop the lowercase r because I was about to write the polar equation for a circle. Here's one equation for a circle in rectangular coordinates. We know that this is very inconvenient because it's a round thing that we're describing with square coordinates. So we might want to use polar coordinates, round coordinates for our round thing. That's certainly more convenient. So we might just say r equals 5. So rectangular or polar coordinates for an equation. Now we're going to describe it. We're going to make a parameterization of the circle. This is even though we have a description all that works for us in R2 already, we're going to want to eventually graduate to R3. So we need to parameterize it. If we think back to our trigonometry, at a point theta in standard position on a unit circle, the coordinates of that point the x coordinate is the cosine of theta, and the y coordinate is the sine of theta. So this is on a unit circle. We can see cosine when theta is 0 starting off at 1 and sine starting off at 0. And then when theta gets to pi over 2, cosine is dropped down to 0 and sine has gone up to 1. And then when theta is equal to pi, cosine is dropped to -1 and sine is back down to 0. So if we want to parameterize a circle of radius 5, if I want to increase the radius, I just have to increase the amplitude of my cosine and sine. Instead of starting off at 1, 0, I want to start off at 5, 0. So I can parameterize my circle by saying x of t is 5 cosine theta, or cosine of t. Y of t is 5 sine of t. If I want this whole circle, I'll have t go from 0 to 2 pi. This will describe a circle of radius 5. Remember that when we parameterize a curve, we assign an orientation to the curve. So if we start off at 0, that means we're going to start our curve at 5, 0 and go once around counterclockwise. Good question. Here I've just listed the parametric equations of this circle. This makes sense. If x is 5 cosine and y is 5 sine, then x squared plus y squared will be 25 cosine plus 25 sine, which will just be 25. So that agrees with x squared plus y squared is equals 5 squared. Also, since x squared plus y squared equals 5 squared, these agree with that description. And also, since x squared plus y squared equals r squared, this makes sure that this description also fits our r equals 5 equation. Nice and backwards compatible. All we're doing is describing this collection of points where x and y are independent of each other and defined by some parameter. Here's how we need to make this work with our line integral. So what we're going to do is, these are the parametric equations. What we will want is a vector function for the parameterization. And that's just going to take the x of ti plus y of tj. So we're going to call this r of t for a vector parameterization. Color code where things come. Contain the same information. I'm expressing it as a vector. A location vector. Any questions? Using our favorite well-known parameterization of a circle. I think all parametric equations examples either start with parameterizing a line like I did last week, and then move on to parameterizing a circle like I did here, or parameterizing a circle and then doing line length. I don't know. Parameterizing a line length, not doing a line. Got to be careful with the phraseology, especially if you were a child of the 80s. Right. Don't worry about it. So here's what we need. This is going to be a vector function giving us locations that will describe the circle. When t is 0, r is the point 5, 0. When t is pi over 2, r is the point 0, 5, and so on. Going around the circle once counterclockwise, starting at 5, 0. If we look back up at the line integral notation, one of the things that we're going to want to do is chop our curve up into small bits dr. I wonder how we're going to get dr from r. If you think we're going to derivative it, that's why we have the d in front of it, then that's absolutely correct. That's going to give us a small discrete piece of the curve that's tangent to the curve. So what we want for the dr is the derivative of our parameterization r of t. Now, I haven't talked about how we find the derivative of this vector function. I'm just going to make you guess. Take a moment and guess. Moment's over. So the derivative of 5 cosine t, derivative of cosine is negative sine, so it's negative 5 sine of t. The derivative of sine is cosine, so this component is going to be 5 cosine of t. So if you're like, oh, do we just take the derivatives of the components? Yes. Your calculus instincts serve you well. The force is so much cooler, like you can do things with your mind and read people's minds and control minds and stuff like that. That last one's a little bit creepy. But you have algebraic and calculus instincts at this point in your mathematical life. Like, oh, is it just this? Yeah, that's your instincts kicking in. This still carries with it the restriction for t. So this is still for t between 0 and 2 pi. That part doesn't change. But that's just saying what values of t that you're going to use. Now, if we evaluate this, this dr dt at these values of t, we're going to see that we get tangents to the curve. So our drs are going to be, let's say when t is 0, we get 0i, so 0i plus 5j. So it's going to be, this is a unit circle. The dr is always tangent to the circle. So in this case, the dr is going to be tangent to the circle. Notice that this says dr dt. That's not exactly what we want. I want a dr, just the dr part. So we're going to get rid of the dt parts. I'll make you guess at how we get rid of the dt parts. No, not quite. I want that dt factor in the denominator. I don't want that dt factor in the denominator. I'm just going to multiply it. So I'm going to say dr is going to be minus 5 sine of ti plus 5 cosine tj times dt. We just multiplied by dt to isolate the dr, because that's the only part that we see in the line integral notation. So here we just multiply by the dt to isolate the dr. Now you might feel that this is kind of fishy, just like when we were doing it before in Calc 1 and you multiplied by the dx and the dy and did all that kind of stuff. You might think that's awful fishy. And my response is, quiet you.
Wait, so what effect does this have on PV5? So
It doesn't. It just works. It's just to make it work.
it's just there to look nice.
It's okay for us to do this. I'm giving y'all permission to multiply by these infinitesimals. But if you're like, oh, this always seemed fishy to me, then that's fine. That is good mathematical instinct. Like, I'll multiply them by these infinitesimals seems fishy. Here's what happens to our line integral. So we have this expression for dr. Here's what we're doing. Remember the plan. Remember the plan. What is this notation telling us to do? We're going to parameterize C. That's just a mechanical thing for us. It's not telling us to parameterize C. That's just how we do it. That's how we tell the integral where we're going to be evaluating our vector field and where the curve is headed. So we're going to evaluate the vector field at all the points on C. So we're going to evaluate the vector field at all the points on the curve. That's what the integral tells us to do. Take all these points on the curve C, plug them into f dot dr. So this is just evaluate the vector field at all the points on C. That is, and since C has been parameterized, it's just f evaluated at all these points, r of t. Now we find the dot product with dr. Dr is going to be r prime of t times dt. R prime is just exactly what we think it would be. Take the derivative of each of the components of R. What we have now is a regular integral dt. So we just evaluate from A to B. I'm going to put t equals A to t equals B. Once we have parameterized the curve, our integral, all the curviness part of the curve is being taken care of with this parameterization. Here's our tangent. These are the little, how we break up the curve into little pieces. And notice that the dt at the end means that we're just doing a simple integral, an integral of a single variable. Also, note, remember, we're going to do a dot product. So this is I and j, but r prime of t also has some I and j. We do the dot product, no more I and j. It's just a function of t. This turns into a function of one variable, and we just integrate it. In this case, we would integrate from 0 to 2 pi, but in general, from a to b. We take our line integral, which seems like such a complicated thing. It's like, oh, it's evaluate this dot product with all these curves. It becomes a function of one variable. All we're doing is taking a regular integral from a to b and just somehow modeling the curviness. Instead of just a boring old interval from a to b, it's now some curve. Any questions? Yes. No, this is not going to give us an area under a curve. If we take this f dot dr, or f of r of t dot r prime of t, if we make a function out of that, then we'll and graph that, then this will give us the area under that curve and between a and b. But it's not, that curve F dot R prime, that's not related to like the shape of the curve. That's gonna be some weird combination of how the function and the tangents along the curve are interacting at all those different points. Tomorrow, we'll do some calculation. It's gonna involve this parameterization. So if I forget, just remind me tomorrow that it was 5. I switched from R to 5. And then what we'll do is we'll come up with a vector field and we'll actually run through the calculation. Then we'll think about what that's trying to tell us. Any questions? Comments? Sniperman? All right, that's it for today. I will see you all on tomorrow. Everybody have a good day and thanks for playing.